All right, welcome. My name is Ryan Holger with Temperature Equipment Corporation, and I'm sitting here today with Bill Bailey, also with Temperature Equipment. This will be our first tag team webinar ever. So not only do you get one of us, you get two of us. So that should be awfully thrilling for you guys. We got a bunch of stuff planned for you today. It should take about 60, 65 minutes or so. And ask us any questions as we go. Just type them in the question box in the bottom right-hand corner, and we'll take occasional breaks to try to read your questions and see if there's anything that we feel like answering or not. All right, fair enough? Good, no one said no, thanks.
Okay. Hi guys, my name is Bill Bailey. I've been with TEC now for about 10 years. I've been doing boilers and hydronic work for about 25 years. Today we're going to talk about practical tips for boiler replacement. If you have any questions, like Ryan said, please feel free to get them to us. We'll try to answer them as fast as we can, and we'll keep this thing moving along for you. Basically, you think about boilers, why would you replace it? Well, the first thing, most obvious, is the thing's leaking. It definitely has to be replaced at that point. Okay, cast iron boilers, very, very hard to fix. Steel tube boilers, you can weld them, but over time, they start leaking. One leak's going to lead to another. That'd be the first thing. The second thing, and probably the biggest reason people are replacing boilers now, is energy costs. Okay, we all know the efficiency standards have gone up. Look at the first slide here. 2012, we had a major improvement. Basically, we went to 82% for hot water and 80% for steam. The two things that you really find out is we did get rid of totally no more standing pilot, and the government required us to have sort of an automatic water temperature adjustment. I think prior to this, most times boilers are basically bouncing off their high limit. So basically any zone would call, it would run up to 180 or whatever the limit was set at, and then the next zone would call it, and all day long, all year long in heating season, you would be running at 180 degree water. So this automatic water temperature adjustment varies from manufacturers, but it's something that's definitely out there, and it is something you're going to have to learn about. It's not just the old TT connections anymore. Okay. As we all know, the energy codes have been changing. Okay, they are getting better and better. This is not going to stop. We all know that. We all know global warming. We know what's going on in the industry. I think we're just starting on this path. My personal feeling is that the days of the cast iron boiler are numbered because of this. Utilities are also playing a big part because of capacity issues that they're having. They are offering more and more dollars to basically go to this high efficiency equipment. That helps them reduce wear and tear on their piping systems, expanding their piping systems and everything else. Years ago they were pretty small, but now when you start getting into these larger systems, you know, when you look at this chart here from Nicor, just 400,000 BTU, that's $1,500. You get to 1,000,000 BTUs, that's 5,000. We start talking some of these bigger boiler rooms, you're going to be talking some serious change. So it is definitely driving the market towards the condensing boiler technology. Okay. There's also all kinds of other rebates out there. Okay, indirect domestic water. We'll talk about that a little later, where it comes in. Tankless water heaters, pipe insulation, thermostats, all kinds of different things out there. Even boiler tune-ups, you're actually giving money back. You have to do it right. You need a combustion analyzer, and you got to prove that you did it. But there is money out there for all these kind of retrofits, all trying to improve boiler efficiency. Just want to touch base a little bit about hydronic system basics. Okay, there's basically 5 components. Me and Ryan do a school on this. It's anywhere from 4 hours to 8 hours, depending on what you want to do. But the 5 main components of the system are basically the load. That would be basically your baseboard, radiators, whatever. The source. Today's discussion is going to be a boiler, but chillers are water also, and heat exchangers are. Okay. The other component of the system is the expansion tank. This is something you really want to look for when you're down in that boiler room. Examine the system, see what they got going. The other next component is the pump. This really should be called a circulator. Okay, we are not pumping water. We are circulating water. We're moving it around the system. We're not raising it like a well. Okay, so it should really be called a circulator, and that's what we're doing. The last component is the distribution system. This is the piping in the mechanical room, the piping out into the system. There's many different methods out there. We don't really have the time to go through them today, but you basically want to walk in there and start looking at what happens in this boiler room and how does this heated water, this source, get out. So you definitely want to take a look at the distribution system. It'll tell you a lot of what's going on in the system. Okay. Expansion tanks are one of the most critical parts of the system. They're definitely oversized most of the time, but they're also very hard for you to resize. Most of the tanks you'll be running into, the boiler rooms we're thinking about talking here today are probably 25, 30, 40 years plus. They didn't have diaphragm tanks back then, okay? So basically an old steel tank, normally it's up in the top of the boiler room ceiling, might have gauge glasses on it if you're lucky enough, so you know what's going on in the system. Probably doesn't, okay? But the expansion tank is there because we are a closed loop hydronic heating system. As we heat water, it expands. If we didn't give it anywhere to go, it would come out the relief valve. Water coming out the relief valve is not a good thing. We don't want to add fresh water to a boiler system. It's the worst thing you can do. So basically, what the expansion tank does is provides you a cushion of air. In the expansion tank you're looking at here, there's a diaphragm in it. That's a purple bladder or rubber piece in there. We all know we can compress air. We all have air compressors, okay? We can't compress water. So basically here, as this water, the blue water expands and gets heated, it will push against that air on the other side of that tank. Once it does that, basically that expansion has been dealt with. There's no issues to it. As the water cools back, the air pressure will push back, and you'll always be in this nice state. Normal residential systems, 12 to 15 psi range. Okay, so basically water heats. As we heat water, it expands. We got to give it somewhere to go. That's what the expansion tank is there for. Another part or common component of the expansion system is the air eliminator. Again, we talked about water a little bit. Water has air in it when it comes in. Water is not good in a hydronic system. It makes noises. Okay, basically you want to call it BBs in the piping or whatever. Okay, that air also, when it gets into an impeller, can cause cavitation issues and actually eat up the impellers. So we want to get rid of air. In the hydronic world, our tricky term is an air eliminator. Okay, basically what it is doing is eliminating air. Also in this drawing you see air separator, same thing. Those are the two that that's what you really want to be using nowadays. Okay, the bottom one is a scoop with an air vent. That was nothing more than a piece of pipe with a bulge in it. And basically on top of that we put a $5 air vent. As soon as the $5 air vent clogged up with crap, everybody shut it off. Now your whole air elimination system was no good because you had none. Once you close that vent, it's over. So most of the air comes from the city main. We want to minimize that air getting in the system. So on our next slide, I think we should talk about proper piping system and where to pipe it in. Okay, if you look at the top picture and the left picture, up in the left picture is probably easier one to see. You'll see by the red dot, there's the actual air eliminator right in the middle. Nice convenient thing I like to do is come right off the bottom of that air eliminator because it has a 1/2-inch tapping right down into the expansion tank with a small T. It makes the system very, very simple. That fresh water is that line coming in, and on this one we're using a little glycol feeder, but that line coming in, if that has any air in it, what's the first thing it sees? It sees the air eliminator. So we're trying to get it out right then, right there, before it even gets into the piping system. If you look at the picture to the right, this basically is the same setup, but instead of having a feed tank here, we have basically a pressure reducing valve and a backflow preventer. If you start where the ball valve is and go to the right, the first thing there is a dual check backflow preventer. Okay, this is required by most codes. Some of the codes in the village have even gone to the point of requiring an RPZ valve on residential systems. So at that point, you have to bring in a qualified plumber and everything else to make sure that valve is certified every couple of years. The next valve next to it is a pressure reducing valve. All our city main pressures normally come in anywhere from 30 to 60 psi. Well, if I put that 30 or 60 psi directly into my boiler, which has a 30-pound relief valve, what's happening? It's going to come right out the relief valve. So what a pressure reducing valve does, just like it says, it reduces the pressure. Normally these valves are set for about 12 psi. The reason for 12 psi basically has to do with math, but basically most buildings, when you get to your 2 flats, 3 flats, even 6 flats with 3 apartments with 3 levels, you get up that baseboard, it might be 20-some feet. If I have 12 pounds of pressure, I have more than enough water all the way up to the top of that system. So that's where now my circulator is a true circulator. We're not pumping water up there. This valve does that. It maintains that whole system. If you run into villages that are requiring you to put RPZs in and costing your customer a couple $100 in inspection fees every year, one thing you might want to do is go to a feeder tank. It is a one-time expense, but it's done forever. So when that inspector comes in after you pull your permits and everything else to replace that boiler, and he finds the feeder tank there, his life is over. We're not inviting him back. We don't have to, because now our feeder tank will automatically maintain the system. And the nice thing with the feeder tank, it will tell you when you do have a leak, because the water level in the tank will go down, or the glycol. So it does help you in that way, but it also helps you get rid of that $200 fee that some of these villages are trying to impose on people as they're out grabbing money. Okay.
Bill, we did have a question come in from Fazal. He asks, for a high-rise building, what is the ideal location of the expansion tank?
In most of your high-rise buildings, your expansion tank you want to find up on the upper floors. A lot of the times in these older buildings, these 25, 30-story buildings, you're going to find the whole boiler system up in the penthouse. But most of the time, you want to have that expansion system, if you can, keep it up at the highest point of the building on a high-rise. It makes the tank smaller in size. You don't have to deal with the higher pressures that would be normally required down in the basement. Okay? All right. This is a typical circulator. Up in the top corner, we're showing the Magnas. That's basically a variable speed circulator. Very nice circulators. They do a great job. They help us with oversizing, because we all oversize circulators. Okay, and we also deal with zones. There's never, very, very rarely in a 6-flat, do you have all 6 apartments calling out at the same time. Typical circular piping, minimally, you want to at least have a shutoff valve on the discharge side of the circulator going to the system. It'd be great to have one on the supply side also. Okay. Minimally, though, I don't like walking in boiler rooms and see no valves on the system. That's just going to cost you time and labor later if you have to work on something. With these more modern boilers, these condensing boilers, the water content is nowhere near what it used to be. Even our 850 mod kind, I think it only holds about 6 gallons of water. So if I had valves on all my shutoffs going out to the system, at the pumps, and also coming back on the returns, I could probably drain my whole boiler in about a matter of 10 minutes. So it's one thing you want to look at. Gauges are a good thing, especially if you're doing larger circulators. But the biggest thing is don't put a bunch of gauges on there. You're actually better off to have the gauge itself with the shutoff valve, or the gauge cock, as it's called right there. Brian's pointing out, have those on there. If you have one gauge and then you have a second gauge, if those gauges are off, you know, one might be a little bit out of calibration versus the other, you don't know that. So if you took the gauge and moved one to the other and opened up and measured both of them, if that calibration of the gauge is off, it's going to be off on both of them, so now you will get a true reading of the pressure drop going across that circulator. Because really all the circulator is doing is taking water from one side, creating a pressure differential, and moving it across the system. So using the same gauge is your best application, and just make sure you have the tappings with the valves so you can do it. Okay, one thing that we always talk about is called right sizing. All right, I've been doing this for 25 years. I have not, to this day, found a boiler that was undersized on a heating system. Domestic water systems, snowmelt systems, maybe, but on a heating system, I have not found one to date that was undersized. Most of them, like we say here, is about oversized by an average of 60%. Okay? Think about it. A boiler is designed to work at the coldest day. The kicker is that's less than 1% of the year, of the heating year. What does most people do? Well, add safety factors. Really think about how a boiler gets sized originally. An engineer, contractor, whoever is in charge of it, this goes back 30, 40 years, did a heat loss calculation. Okay? Once they did that heat loss calculation, they specified a certain boiler, and they picked the size. Well, this is how things started getting out of control. Okay, the winning contractor then picked that boiler, goes to his favorite wholesaler, finds it, and the wholesaler says, hey, you know what? You need a 250? I got 300s, and they're less than 250, and I got a big sale on them. I bought too many. So now immediately what happens is that boiler just became 50,000 BTUs bigger than was actually necessary. So now 30 years later, we're not even talking yet, but 30 years later, somebody else goes in and just looks at that tag. And the wholesaler has another special deal. So this is what just keeps happening and happening and happening. That little boiler on the right over there is probably about 40 years old. I actually did a radiation count in that residence. The total connected load was about 78,000 BTUs. That boiler itself is 198,000 BTU input. If you don't think that thing cycles, you just hear it. Okay? When we're cycling, the biggest thing that happens is we hurt the equipment. Cycling is the worst thing. It's just like stopping and starting your car every 5 minutes. It's not something you want to do. So we want to get rid of cycles. That's why it's very, very important to size this equipment correctly. Okay? The equipment will always operate better when it's in like a cruise control mode. You'll see that becomes much more important in the modulation stuff, in the high efficiency boilers. Also, if you're the smart contractor and you don't go in and just read the tag, you're going to have a smaller boiler. You will definitely have a smaller boiler. That means the first cost is less money. That means your bid should be a little less money than your competition that just went in and looked at the tag. Because all he's doing is repeating the mistakes of the past. So you will have a lower first cost. It might take a little bit of explanation. But the easiest way to talk to people is to say, hey, last year, classic, one of the coldest years around, was your boiler constantly running? Most people will say no, because it's not. It was oversized to begin with. So you went through the worst year and you never saw your boiler continually running. That means it's oversized to begin with right there. If you got to prove to them, when we go through how to size these boilers, pull the paperwork out. It's pretty easy to explain to them how you got this size. Okay. There are different sizing methods. All right. Basically, heat loss calculation is the best method. Manual J is residential, ASHRAE's for other methods in commercial. Load counts are required by code on a lot of new applications nowadays, and even older ones. You got to prove that you're there. The biggest problem with a true heat loss calculation Manual J is we don't know what's in that wall. We can make assumptions, but assumptions aren't good. All right? You don't know what's in that wall. You don't know the insulation value. We all know windows have been improved. Attics have had more insulation added, but we really don't know what's in that wall. That's a big component of the heat loss factors. So the heat loss, if you have all that information and it's good information, that's your best method. You will come up with the right boiler size. Boiler tag comparison, this is the worst method. Just think about it. You are going back and assuming what the last guy did was right. You're not assuming that they did anything to help the place, and you will be definitely oversized. There's just no doubt about it. You go in and look at that tag and do the same thing that everybody else did, you'll be in trouble. You'll have the same thing. Okay? Radiation method. This is basically, you can only put so much stuff in a 12-pound bag. Okay? So what we're doing here is, it's not as accurate as a load calc, but can be done with a lot less input data. It's also pretty easy. This requires no more than a tape measure and basically a lighted mirror or whatever to double check the baseboard. There's less oversizing than simply reading the old tag, and like we bleed it out here, you can only put 12 pounds of you-know-what in a 12-pound bag. You can't put more BTUs into a system when it doesn't have that amount of radiation available. Okay, so that's the typical. What are you going to find on a typical boiler? Basically, there's going to be 3 ratings. The first one's the input. That's the easiest, most straightforward. That is the actual consumption of the boiler based on what the manufacturer says. The next one was always the Btu output, or you'll sometimes see it called the DOE output. The DOE was Department of Energy. This was basically the government coming along and saying, hey, if you're telling me this boiler is 80% efficient, I'm going to do a little math here. I'm going to take 100,000 BTUs times 80%, and per the Department of Energy, I'm going to have 80,000 BTUs of usable heat to the system. Okay. The last thing you're going to see on tag is a net IBR number. Now, IBR stands for Institute of Boiler and Radiation. This is a group that goes back to the 20s. Okay. Before then, every boiler manufacturer say, hey, I'm going to put 100,000 BTUs in the boiler and I can get 70,000 out, or I can get 80,000 out. And they had no way of really knowing it. So it was basically a real crapshoot then buying a boiler. IBR, the Institute of Boiler Radiation, a bunch of manufacturers got together and said, okay, we got to start standardizing that stuff. You know, you cannot have 500 pounds of cast iron, you got 500 pounds of cast iron, and you're getting 1 million BTUs out and you're only getting 500. There's something here. So basically set up some standards. One of the standards they set up was the 180, 160, which means water goes out at 180, comes back at 160. They also did an arbitrary number. Back in the day, there wasn't really much for insulation, so they basically decreased anybody's output by 15%. Okay, that they basically said was due to all the piping, startup load, and everything else in the house. Right? They considered that totally not usable, even though it was within inside the basement or the hallways or whatever, if you're dealing with schools. But they basically just chopped that right off. So you'll see that that 15% is basically a function of your 80. So basically you're looking at probably, in this example here, you'd have an IBR rating probably in the 65 to 67,000 BTU range. Okay, but those are the three numbers you're going to get on the tag. All right. Equivalent direct radiation, or EDR. If you think about it, what this is a term that if you were to take a radiator or any piece of hydronic output equipment, your baseboard or whatever, and laid out all the surface area, how much actual mass is there or whatever that's going to give off heat. Okay, even though a radiator's columns, we have radiant heat that comes off of it. When you get near a radiator, you don't have to touch it. You know it's warm. We also have convective heat. That's when the air is going through the sections, it's picking up some more. So even that stuff that your body doesn't see, we are still getting some heat off that due to convective airflow. Now, radiator covers and that reduce that, but for our discussions, we really don't worry about the covers that much. We want to know how much heat that actual radiator can put out. EDR is the term that they used and how they figured it out from years ago. Okay, more surface area, like we say here, equals more heat transfer area. That's why you think about it, a radiant floor system is one of the best heating systems because of the amount of surface area we have. You do a large manufacturing firm or whatever, 100,000 square feet, you got a 100,000 square foot radiator you're walking around on, it's going to keep you warm. You put a bunch of little terminal units on the wall, they're going to have different areas, different amount of heat output, but now you're doing convective, maybe you have fans on it, you have different things going on. But basically, you're trying to find a number, okay? That 1 square foot of EDR, we don't care how we get to it, it's going to give us a certain amount of heat. Now, we talk about steam here, okay? But for 215 degree steam, which is about 1 to 2 psi at most, you're going to get 240 BTUs off of that square foot, off of that 1 square foot of that radiator. When we're dealing with water, that number drops dramatically because we've got to remember water, we're looking at 180 degree supply water temperature. At that point, we get about 170 BTUs an hour. Okay, so that's the number we always remember. At 180 degrees, we get 170. Were there systems out there running 190, 200 degrees? Yes. Okay, that's not the typical. Most of the time that happened because people were having issues heating stuff, people weren't cleaning radiators, people weren't cleaning baseboards. So instead of taking care and doing the normal maintenance and getting all the gum out of the convectors in the classroom and the crayons and the pencils, they would just raise the temperature of the boiler. So when you go down and see boilers at 190, 200 degrees supply water temperature, I will guarantee you start looking at those classrooms and those radiators and you'll find a whole slew of interesting little critters and creatures and whatever in there. So instead of doing proper maintenance, what happened was it was easier just go turn the aquastat up on the boiler and solve your problem. So we're going to have to get away from that. And we'll talk about that more. When we're doing radiant floor, most people ask, well, how do I know what the tubing is, what the spacing is? The tubing and spacing are critical to the system, but really what you got to remember, the tube is not the radiator, the floor is the radiator. All right? That actual floor is your radiator. So the ultimate highest number, and this is just going back, way back, about the most, absolute most you can get out of radiant floor systems, about 50 BTUs a square foot. Now remember, we're just calculating here. We're not trying to nail this boiler on the head. We're just trying to make sure we get realistic with the thing. So if you use 50 BTUs a square foot on a radiant floor system, that is the most you're ever going to get out of it. If you start trying to go past that, you're going to be on a dance floor because the floor is going to be way too warm. So that's a safe number to use. Yeah, our boiler might be a little bit oversized because of that number, but we're going to be a lot better than what happened years ago. Okay. Baseboard. This is very, very critical. It's very easy to mess up because basically what you really got to look for in baseboard is look at the fins. A piece of copper pipe itself has very, very little output, okay? So we don't want to know that. If you think about how most apartments were built back in the 70s, early 80s, when there's a boom of them going on, these 6-flat, 12 flats, they basically ran the baseboard wall to wall. So on the bottom here, we show you about a complete baseboard, all right? The kicker is that baseboard's running wall to wall. What we really want to know is that 16 feet of active length. That's the heat emitter. Those other 2 feet on each side do nothing. Why'd they do that? It's a lot cheaper to run a little extra piece of cover here and there than have a trim carpenter come back in and basically finish out trimming out little 2-foot pieces everywhere. So they ran a lot of what's called blank cover. For our system, what we need to know is that active length. If you go in and just measure the baseboard, I'm going to beat on this one, but if you keep measuring just the baseboard cover, you will be wrong. You've got to get that active length. That's where the little mirror, you get them at Home Depot with the lights on it, and you just take that thing and go right underneath the baseboard and look where the end is and the finish is of that fin tube. Then you take your measurement. That's what you want to know. Residentially, most baseboard runs 500 to 600 BTUs a foot for the active length. So that's the number you want. So if I go in there and I got 20 feet of baseboard covering the wall, but there's only 10 feet of active length, that means I only really have 6,000 BTUs coming out of that piece of baseboard. If I did it the other way, I'd be in trouble. I'd be thinking I have 12,000. Now what happens to my system? You're going to be oversizing your boiler again. So you got to really watch that active. Commercial baseboard, 800, 1,000. Some of the higher stuff with 2 rolls in it, you're going to pick up more. Okay? If you're not sure, you don't have to get the exact manufacturer. A lot of the commercial baseboard was very similar. Find somebody's brand that you like. I prefer the slant fin brand that we handle here. And basically I have a very, very good book on commercial baseboard that tells you the different heights, the different styles, and what kind of outputs you can get. So it helps you make that much more accurate. But if you're just roughing one, seeing where you're at, 800 or 1,000, you'll be safe. Okay. Radiators are probably the hardest thing to work on, all right? Because you're sitting there and you're figuring, how am I going to figure out all these little things, all these little ins and outs, pieces missing, and everything else? Well, the old guys they figured out years ago, pre-computer, pre-everything. The way they used to do it was they would take that radiator, actually dip it in a vat of paint. They would measure, they would know the weight of that vat, the weight of the paint. They would dip it in, pull it out, let it drip off, and basically then take that amount of paint, the difference, take that amount of paint, and swear to God, they would actually paint the floor. And then they would count the square footage, and that's how much they had. Because they knew that layer was very similar to that layer that just stuck to the radiator. It sounds ridiculous, but it worked. A few years back, they did an experiment to see how close they were, and these guys were within about 3 to 4%. That was the old method. Okay. There is also a book out there called EDR. It's called Every Darn Radiator. You can get it on the web. Very, very good book. It's probably about 300 pages, and it shows all these radiators and gives you all this square foot radiation or EDR numbers. What you're doing with a radiator, here's where the tape measure comes in, is basically you're measuring the height. Okay? You can measure the width, or you can count the number of tubes or whatever in there, you know, or columns, however they want to call it. Okay? And then you go over to one of these charts, and it'll say, okay, for a 20-inch high radiator, and I have 2 columns on it, I'm going to have 2 square foot of radiation per section. Now in our little radiator here, if that's where I'm at, I times it by the 4 sections, and that tells me basically I have 8 square foot of radiation. So if I did my paint thing, I'd be able to paint out a 2 foot by 4 foot square on the floor. And that's my 8 square feet. Now I take that 8 square feet, times it by 170, and I know what that radiator can put out. So let's just make it easy. Let's say it's 10. You know, we're going to be at 1,700 BTUs. It's a 5-section radiator. So if I got 1,700 BTUs and I try to shove 3,000 in it, what's going to happen? Nothing. I can only get 1,700 out. So that's why we try to do this method. We're going to go around and count all these things up. Okay.
All right, and then we add up all the radiators or all the baseboard and sum them up, and that's the maximum amount your boiler could possibly shove in there. You couldn't possibly need a bigger boiler if you wanted to. So it's not uncommon that you'll go around a building and you'll count up 80,000 BTUs of radiator and have a 200,000 BTU boiler. Where the hell are you going to send the other 120,000 BTUs? You have nowhere to send them. All right, we're going to ask our first poll question for you PDH guys. I'm going to launch it right now. All right, so what are the potential benefits of correctly sizing a replacement boiler? Check all that apply. Longer run times and less temperature swings, lower first cost, longer equipment life expectancy, lower utility costs, more floor space. And while we're doing that, I'll read one more question that came in and see if we can have Bill answer that from Fazil again. What is the fill pressure required in this system for that high-rise building type example? If the building static pressure is higher than the fill pressure, can the fill makeup be relocated at a higher elevation?
Yes. You can put the fill makeup at the expansion tank up near the top of the boiler in that penthouse application. Okay. When you're talking these kind of buildings, yes, we definitely want to engineer it. We want to look at what the actual height of the building is, so we don't oversize the system, overpressurize the system. But yes, most of the time you will find the expansion tank, the air eliminator at that point also, because that's the highest point in the building. That's where air naturally goes. And we'll put the pressure system up there also to maintain the static pressure. What you're doing in any building is basically we want to make sure we have water all the way up to the top radiator. Normally you're looking for about 4 to 5 psi above that radiator, which gives you good pressure in the system, because that pressure will help us make those bubbles in the system smaller, thereby easier to get out. Okay. Once we get the air out of the system, we got a great hydronic system that's not going to make noise or anything else. Okay.
All right, so the answer to the poll question is actually all 5 of these. All 5 are actual benefits, right? So most of you guys got most of them right. Some of you guys did not recognize a few of the opportunities there. But you definitely will have longer run times if the boiler is more correctly sized. It'll be a little bit smaller than it otherwise would have been, which means less temperature swings. It should be less money to buy a smaller boiler than a big boiler, right? The equipment should last longer. The more times you cycle any piece of mechanical equipment, the sooner it likely is to die. You should have lower utility costs by running at a more stable, steady state condition instead of cycling it on and off. And in most cases, boilers are smaller than old boilers, and if you have less of them, they're even more small, right? So you'll actually have more floor space as well.
And you'll see that floor space disappear. Once those church ladies figure it out, it's taken over. So talking about higher efficiency is the main driving force for this whole thing. Condensing boilers are really the way to go, okay? They were introduced into the market right around 2000, 1999, 2000. Before that, there were a few manufacturers out there that were dabbling in it, not with much success because the costs were so high. And back then, you think about early 2000, gas prices were pretty low and pretty stable. But around 2000, they started getting a little more serious about it. Again, reducing the fuel bills was a big thing. We can combine them with older type boilers. Remember, all a boiler knows is it's being told to heat water to a certain temperature, but it's being told to heat water. That's all it knows. It doesn't know where it's going, what it's doing. It's just heating water. Okay. A couple things with condensing boilers, though, they do need to be cleaned on a regular basis. If you want to maintain that high efficiency, and this goes for furnace or any piece of equipment, if you don't maintain it, from day one you're going down. Other thing with condensing boilers, if you don't know how to do it, get some training. If you put in a boiler just like Grandpa did, a new condensing boiler, you will have issues, guaranteed. They do not pipe the same way. They have other controls on them. There's a lot of different stuff here. This is not a typical, it's not your old cast iron boiler, water in, water out, okay? So do get some training. If you're not, we've got classes all the time. Ton of them. We're more than happy to show you. We're more than happy to train them. We're more than happy to go out with you on job sites. Worst thing that happens is people come in, wrong piece of equipment, or piped incorrectly, and that piece of equipment's a piece of you-know-what, and it has nothing to do with that piece of equipment. Okay? One of the biggest things when you are dealing with condensing boilers is venting is totally different. Okay? Since these boilers are running very low temperatures, we are using a lot of times CPVC, Schedule 40 PVC. Some guys still use stainless, pretty pricey. But the venting is totally different because you got to remember we are condensing. People say, well, my system's designed for 180. When does that 180 come up? 1% of the year. The rest of the time we can be running much cooler. That's why this venting is very critical. You can't just dump it up the old flue, okay, because your flue will be basically raining, and with a matter of years that chimney will be on the ground. Okay, so venting is very critical. You have to follow what the manufacturer says as far as links, because these are basically a power burner type situation. Right? So basically there are limits to how far you can shove that flue gas.
Every one of these condensing boilers is going to need its own dedicated piping as well. Generally speaking, you cannot share chimneys and exhaust stacks between condensing boilers. They have inducer motors on there that run at reasonably high pressures, and if you have two of them on the same vent pipe, one of them will backfeed into the other. So if you see over here on the bottom left, we got 5 boilers in this drawing. We got 5 intake pipes, all right, and 5 exhaust pipes. Everybody gets their own pipe now. Sometimes what we do on buildings is if we can't get out the sidewall like we did over here on this side, is we'll actually go up the old chimney. We'll use your old chimney or your old exhaust stack as a pipe chase for all of our new PVC piping. Right, we already got the hole there. It's already running up 2-3 stories. Why not go ahead and use that, right? We'll have dedicated PVC pipes, but we'll use the chase as kind of a the old exhaust pipe as a chase for all these new ones.
Okay, venting is one thing is critical. Piping is also very critical. Okay, this is where we had, back in 2000, a lot of our problems. Okay, the piping arrangement may need to be different, but most of the times when you're dealing with a low mass boiler, they definitely need primary, secondary piping. Okay, it just keeps you out of trouble. There are some boilers that have it built in, that's great. Okay, if you're not sure, build it in. You ain't going to hurt yourself. All right. But basically in here, this is typical primary, secondary, very simple application. We're showing the circulator or pump number 1, our expansion tank. There's our boiler, high efficiency boiler. Basically all that pump is concerned about is the pressure drop of that boiler. These low mass boilers have a very high pressure drop, so they cannot deal with that second pump or that pump that was originally there to handle the whole system plus the new boiler. So basically we got to go to a primary, secondary type piping. Okay, and this shows you here. The biggest thing with that common pipe space there, that has to be as small as possible. The normal rule of thumb is 4 pipe diameters. So if your pipe, that boiler is, let's say, a 2-inch pipe, all right, A to B has to be a maximum 8-inch center line to center line. Has a lot to do with primary, secondary piping. We don't have a lot of time to get into today, but keep those T's as close as possible. Maximum 4 times the pipe diameter. You'll have no issues.
So basically pump number 1 in this case is responsible for only the pressure drop of the boiler and the boiler room piping. Pump number 2 is responsible for the pressure drop of the building, and they have absolutely nothing to do with one another. If pump number 2 is off, then all the flow goes to this primary pipe only, just this loop. If pump number 2 actually turns on, then the flow would take this path and make a right-hand turn here and go all the way around this loop. I'm as good of an artist on this computer as I am on a whiteboard. All right, move along.
Okay, here's another way. In the top left, we show you closely spaced T's. As you can see, there's probably a 1/2 inch in between those 2 T's. That's exactly what you want. Okay, another method is a boiler buddy, as you see in the bottom left. If you look over to the right side, that's basically inside of it. It is nothing more than a buffer tank. That's what we call it that. It's a vessel of water. That's it. So we pipe in and out from the boiler to the tank, and we pipe out of the tank to the system and back around. So now our boiler does not cycle as much because instead of seeing little zones, it's seeing 30, 40 gallons, whatever the buffer tank is designed for. That's where we're going to store our BTUs. These buffer tanks are super insulated. Even if they're running 180 degrees, you can have your hand on them all day long. So we're not losing energy from them. It just makes that boiler run longer when it needs to and cycle a lot less often. Hydraulic separator is just another method of doing it. Okay, they're very popular in Europe. It is doing the same thing as a buffer tank, just on a smaller version.
Yeah, so your easiest, low-cost way is the closely spaced T's. You absolutely have to do that. The hydraulic separator is just a fancy way of doing the closely spaced T's. And the boiler buddy is nothing more than a hydraulic separator that also gives you that buffering capacity that Bill was mentioning. So depending on your project, you may do it any one of those different ways. The efficiency of boilers, condensing boilers, is the main driver on why we want to put them in. Yeah, we have to change your boiler out because your boiler's dead, but we'd also like to save you some energy in the process over the next 15, 20, 30, 35 years. Most of the boilers we take out of a building are probably about 80% efficient, right, when they were brand new. A lot of times they'll be less than that. The dirtier the heat exchangers get, the less efficient they are. Additionally, older boilers weren't even 80%, right? So if you get boilers that you're taking out from the 70s and 80s, they may be 55, 60, 65% efficient. So you want to find out how efficient the old boiler is that you're taking out, and then how efficient the new boiler is that you're putting in. And with that amount of information, you can quickly calculate for people how much money they're going to save, which is obviously the first question they're going to ask you when you mention a condensing boiler. Additionally, if you add outside air reset to a boiler system, you could save another 10 to 15% energy. We'll talk about that in a minute here as well. There are 3 different terms of efficiency that we use in the hydronics world for boilers. There's combustion efficiency. So this is if I take my gauges and I measure the air temperatures coming through the exhaust pipe, I can calculate the efficiency of the boiler, right? So this is basically, I measure how much is going up the stack. I assume everything else is going into the building, right? Thermal efficiency is kind of the opposite. We use the temperatures of the water going in, so we measure basically what's going into the building, and we assume everything else is going up the stack. The difference between combustion efficiency and thermal efficiency is the boiler jacketing itself. How much heat is that boiler losing on the jacket? AFUE is the residential version of that. It's kind of like thermal efficiency, but we take into account cycling losses, whereas combustion efficiency and thermal efficiency are steady state conditions. For the purposes of today and for the purposes of explaining to a building owner or a homeowner, it doesn't matter, right? I don't care if it's 94% thermal efficiency and 95% AFUE. When I start talking about the money they're going to save, it's a guesstimate anyway. So any one of these numbers that I get off the tag is going to be sufficient. One of the ways that we like to do it is with a simple hand calculation. We used to do this on paper. Now Nicor made nice little cards for us that we can use to do it. But basically, you got to get someone's utility bills, basically for the winter months, right? So October through April for most buildings that are light commercial and residential. So if I go to someone's house and I get all their bills from April through October, and they're buying $2,500 of gas, that's nice, and I know that, it's wonderful, assuming they can give me their bills. But I also need one of their summertime bills, right? I need that because I have to back out all the gas usage that has nothing to do with the boiler. Water heating, stoves, dryers, whatever. All right, so I take those $50 times the 7 months, $350 out of the $2,500 has nothing to do with space heating. That means $2,150 is space heating. In my example down here, I'm going from a 70% boiler to a 95% boiler. I save 25%. 25% of $2,100 is $530. You can that simply tell someone how much money they're going to save by going to a condensing boiler. You need to know approximately the old efficiency. You'll definitely know the new efficiency of the new boiler. And the hardest part is they got to gather up some bills from the past year. If you add outside air reset control, it's probably about another 10%, right? So it's another $50 on top of the $500. There's also plenty of tools you can use to calculate if people want to have a nice, pretty report. Sometimes chicken scratching this on a napkin isn't good enough for them, right? So they want an official-looking report. Residentially speaking, there's an Energy Star calculator that's freely available. You can download it. It's a spreadsheet, and it spits out a nice little report. Commercially, you'd be looking at more energy modeling type tools and stuff like that. So if you look at the efficiency of boilers in general, right, it depends on what temperature water you're working with. So down in the bottom of this chart, we go from 40 to 240 degrees of inlet water temperature to the boiler. That's my return water temp. Up the left-hand side, I got 80 to 100 degrees, or excuse me, 80 to 100% boiler efficiency. So when I take a typical 180-degree supply system with typical 20-degree delta T on the radiators, that means I got 160 coming back as my return. This particular boiler we're looking at is an 86% efficient boiler. This is just a generic boiler out of the ASHRAE handbook, but you get the idea. If I ask him to make me hotter water, his efficiency will decrease. If I ask him to make me cooler water, his efficiency will increase. Then when I get to about 130-degree return water or so, a magical thing happens, and I actually am able to have cool enough water that it condenses the flue gases. And then that latent energy of the flue gases stays in the heat exchanger. And I get to save that energy instead of letting that energy go up the stack. Those flue gases are going to condense somewhere. They can either condense outside when they hit the cold air, or they can condense inside my heat exchanger, and I save that heat. I want to condense them inside the heat exchanger, right? So then my efficiency spikes up very dramatically. And if I give it really cool water, like 80-degree return water, all of a sudden my 86% boiler is a 96% boiler. It's a pretty dramatic difference. But look at a more specific boiler, right? This is a boiler we had in our lab here in Melrose Park. And if you didn't know it, we have hands-on classes for all this kind of stuff. But this boiler with 160-degree return water at 100% fire is a 93% efficient boiler. It's a very nice mid-tier, condensing boiler. And if I ask it for cooler and cooler water, it gets more and more efficient. When I get to 130, it does spike up a little bit. Not as dramatic as the regular boiler because it's already really efficient, but it does spike up at a little bit of a faster pace. So one way to save energy is to turn the water temperature down on the boiler. The other way is to lower the firing rate of the boiler. If I have a heat exchanger that's, X big, and I lower the flame size, and I still have that big heat exchanger, it's going to take me less energy to heat that surface area. So if I lower the firing rate, in this case yellow is 100%, magenta or pink or whatever that is 2/3 firing rate, and blue is 1/3, right? So even at peak water temperature, if I tell it to run at a lower firing rate, I can go from 93 to 95%. I can pick up 2% of energy savings just by keeping the flame low with a modulating type burner.
Okay. Outdoor air reset is also very critical. Every condensing boiler we have out there nowadays does come with outdoor reset built in. Okay, I remember what we were talking about a little earlier about that 1% time. 1% of the year you're actually at your max output or your max Btu load. So that means the other 99% of the time you don't need 180-degree water. This is what outdoor air reset does. It basically says, okay, at a certain point along this chart, depending on where you want to go, if you look at a little star maybe, in the middle, let's say that's 140-degree water temperature. So maybe at 45 degrees outside, I only need 140 to keep my building warm. So what's that doing for me? That's basically making the system run more efficiently at a lower temperature, so I'm putting in less gas into the whole system, and I'm not bouncing off of 180 all the time like I do with the standard condensing boiler. So outdoor air reset, once you set up your 2 points per se, at 0, what's my max temperature? 180, and at 60 degrees, what's the water temperature I need? In this example, we're using 120. So anywhere in between that, now we're saying, okay, at 45 degrees, I need 130. At 10 degrees, I might need 170. All that time, you're sitting there saving energy because you're not bouncing off of that 180 like every cast iron boiler is doing in existence today. Okay, so outdoor air reset is part of all these condensing boilers because they always want to be running as low as possible. That's why most of them have these 5-to-1 turn down rates, which means you could have a 100,000 BTU condensing boiler. It could be running at 20,000 BTUs, and it could be running there all day. So one thing that people will get a little freaked out about is they'll say, hey, my boiler's running all the time. You ask them, hey, let me show you some. Look inside this little sight glass here. And you see how small that flame is? It looks like a bunch of little match tips. Instead of being 100,000 BTUs like your old boiler, it's just kicked on and off and banged 100,000 BTUs on. This thing's sitting here and it only needs 20,000 BTUs an hour to heat your house. So that's what outdoor air reset does. It basically helps us modulate as low as possible. So like Ryan showed you on those other ones, on other graphs, raises the efficiency as much as possible. That's the name of the game. Okay? When you start looking at radiant floor systems, there's no reason you should not have a condensing boiler in a radiant floor system. This is perfect application. It always likes cooler water. The boiler likes the cooler water. That's what you're doing here. Okay? So radiant floor systems, if you're not putting a high efficiency boiler and you're doing it correctly, you're actually going to cost yourself more money because you need some type of mixing devices, controls, and other things to add to that condensing boiler so it deals with its stated lowest temperatures that it can run at and not avoid the manufacturer's warranty. You can't run a cast iron boiler at radiant floor temperatures. You will definitely kill that boiler in a matter of years because it will be condensing and it's not designed to condense. So radiant floors, you should have condensing boilers if you're really doing your customer justice.
And by the way, if you think radiant floors with 80-degree return water are good, imagine what a snowmelt with 40-degree return water looks like in terms of efficiency, right? It gets really, really good. All right, we got our next question here. I'm going to launch it right now. How efficient are most condensing boilers? 60 to 70% efficient, 80 to 90%, 90 to 92%, 93 to 96%, or they are very efficient. I'll give you a clue. Very efficient is not a good enough answer. While we're looking at that real quick, we'll just see if there's any more questions we could try to answer on the fly. Mohammed asks if can flue be discharged at a little above grade level. So if you want, Mohammed, I can send you a chart on what the National Fuel Gas Code requires for different exhausts, and you also have municipal codes that are involved in that too. So some towns, you only got to be a certain number of feet above grade level. Other towns, you may not be able to do it at all. But yes, in concept, the answer would be yes, Mohammed. You can discharge the flue at ground level, but it may depend on what's near there and what codes you're following.
And you also got to watch out for the snow conditions. It's just in most of the manufacturers' installation manuals ask you what the normal snow condition is, because definitely we want to be above that. We're not using the exhaust as a snow melting system here, so be careful with it. Definitely be careful when you're dealing with people in the Chicagoland area with the new codes. A lot of the residential and small commercial applications, sidewall venting of flue gases is being very much discouraged, if not outright banned. It's a little bouncy right now, but I think the city was getting a little tired of people in certain areas blasting flue gases back and forth at each other. So that has happened.
All right, so the answer to the question was D, 93 to 96% would be most condensing boilers. You could have some down at 90, 92, but there's not very many there at all. And you could have some up at 97, 98, not very many there. 93, 96 is, the vast majority of the market. And then anything below 90 is not going to be a condensing unit at all. All right, there are a few more questions here. We'll try to circle back around to them if we get time. But we want to go ahead and continue moving through some of these slides here and talking about a few of these different boiler types.
These slides are here for your use. There are different types of condensing boilers. Basically, there's two types we're going to discuss today, low mass and high mass. Low mass boilers, basically exactly what it says is low mass. There is not a lot of water volume in these boilers. Okay, they can be wall or floor mounted. As you can see, the efficiencies, 550 to 200,000 BTU, 2 million BTUs. Most boilers do modulate on a 5-to-1 turndown rate. Since we are condensing, we have to use materials that will deal with it. This condensate is corrosive. So basically, stainless steel is one of the most popular, copper, nickel, or aluminum. These boilers also are a lot quieter than the old days. One thing we do when you talk to us about a boiler is we will make sure on these low mass boilers, since the tube passes are very small, that we will provide you with strainers. Very, very critical. You plug up these tubes in this boiler, it's over. There's no going back. So we make sure you put that strainer in and be able to maintain it. Okay. This is just a couple more examples of low mass condensing boilers. These things are smaller. That's why earlier we said yes, you will save floor space. They are a lot smaller compared to what you're used to. That means they're also a lot lighter. So for older guys like pushing high efficiency, it's a lot easier to move into the boiler room. But basically, the event was scheduled 40 PVC. Some do require stainless steel venting yet. Okay. Most boilers do have built-in sequencers for multiple boilers. All of them, like I said, should have outdoor air reset. Without it, you're basically cheating your customer. A lot of them will stage or do lead lag. And almost all these boilers have domestic hot water priority. It's just so simple to do it off these high-efficiency units. Now you've got a high-efficiency domestic hot water heating system. These are just some pictures from our lab of different boilers. On the far right is a smaller boiler. You can see the tubes over there, little ovals. That's what we're talking about. That's where the pump and pressure drop is coming from. Those are small tubes. We've got to make sure the debris is out of them. What Ryan's circling right now is those are the actual tubes looking at from the fire side, if you want to call it that. And above you is actually the burner itself with the gas valve and the blower motor. The furthest picture to the left or to the right is actually just showing what the whole front of the boiler looks like after you take the cover off. So it's a lot different than the old cast iron with atmospheric burners. This is a job we did years ago. We took millions of BTUs out. This is not the whole boiler room. There's actually a couple more boilers here to do the heating. Then we did some air handlers in the hallways, and we also did the domestic hot water for this whole building. So we basically took out some 60% efficient boilers at best and went all high efficiency.
The nice thing about these is this is on the 30th floor penthouse of an apartment building, so it was really easy to bring these things up the elevator. So the modular aspect of these smaller condensing boilers is really great for retrofit scenarios. Some of these modular boilers also, depending on the brand and manufacturer, might have piping packages available with them just to make it a little bit easier to gang them all together. There's lots of different ways that you can do that. And saving space is typically a key factor in some of these mechanical rooms. If we can get you the required amount of BTUs and less space, it's usually a good thing. All right, let's launch our third question for you guys here. What is approximately the coldest return water temperature we can have to a traditional boiler, and what is the coldest water we want to see at a condensing boiler? So the choices, as you guys are already seeing on your screen, is 180 for traditional, 140 for condensing, 140 for traditional and 40 for condensing, or 140 for traditional and 90 for condensing. What's the coldest one for both of those types of boilers? Give it another few seconds here. 50% of you have voted. And I'll close it in 10 seconds. 3, 2, 1. All right. So only a little more than half of you actually got the correct answer. The correct answer is about 140 degrees for traditional boilers. You can kind of push your luck with 130 maybe. Just kind of depends. You'll be on the fringe of condensing there. But for condensing boilers, so a lot of you guys chose 90 as the minimum, which is, it can definitely be way colder than that, right? We can take it down to 32.1 degrees, basically. If it's not frozen, we can pump it. Condensing boiler, the colder the water, the better. As long as it's not so cold, we can't pump it anymore. So 40 degrees would be the right answer. B. 140 for traditional, 40 for condensing.
Where you're going to see that 40 degrees is basically if you're using a condensing boiler to make domestic hot water and or snowmelt systems. So when you're designing a snowmelt system, you got this condensate to get rid of. Make sure you got a decent sized drain available, because when they first start up, they condense like a bear. Okay, which is fine, and they love it. So,
and just so you guys can see real quick, since so many of you guys didn't get that one, right? On that chart, we want to go as cold as we possibly can, right? So if I get it from 90 to 40, I'm going to get another, in this example, 5% more efficient by doing that. So I definitely want to take that 40 degree water if I can get my hands on it. Nothing wrong with that at all. All right. A few more different things we'll touch on here.
okay. Earlier we talked about using the chimney as a chase. Well, when you do that, there's one drawback. Basically, you've got to deal with the domestic hot water system. Most of the times you just have a small, if you think about church, you have maybe a 50 or an 80 gallon water heater that's dealing with the bathrooms in the church, maybe a small kitchen that's used once a week or whatever. Well, if you use that chimney for a chase, you got to do something with the water heater, because you cannot just dump that flue gas up next to all that PVC pipe, because basically you'll just have PVC goo within a matter of time, and it won't be that long. So basically a very simple way to do it is to go to an indirect storage tank. This is nothing more than another zone off your boiler, very small. Normally when we're doing a lot of these churches and that, I'll take a 50 or 75 gallon water heater and knock it down to a 45. Just because of, got to remember, I've got a boiler over here that might be a 500,000 BTUs dumping into that little Cooper nickel heat exchanger on the bottom, transferring a ton of heat into that tank to make up the water. This gets rid of the whole flue issue. If you're talking residentially, what this does is basically now you have a lifetime warranty water heater. Talking residential, or not residential, commercial, basically you're at about 7 to 10 year warranty. What you do have is super insulated, think of it as a thermos bottle water heater. And it gets rid of that whole flue issue for you for the gas-fired water heater. We really wouldn't want to see you going electric just to make up that load. So it's very easy for us to do this off those condensing boilers. This shows you an example of it. This is pretty it's not really complicated if you break it down, but there's that indirect domestic hot water storage tank over on the left, and then basically we have our boiler on the right side. And what happens in this application, and we do not add BTUs for the domestic hot water, we prioritize it. So when that DHW sensor calls for heat and says, hey, that water's too cold, goes to the boiler and says, okay, boiler, I need to make domestic hot water. Forget your outdoor reset curve. I want 180 degree water now. I want you to turn on pump 2, at P2 there, shove all that boiler hot water into that coil in that tank, shut off P1, I don't care about the heating right now, and heat up that water in that tank as fast as possible. Normally these tanks take maybe 10 to 15 minutes to do that. I've even seen 119 gallons indirects heat up off a system in 20 minutes from a cold dead start. We brought 40 degree water into it and jacked it up to like 130, 140. So they're very, very fast. They're very efficient because you're looking at very cold water temperature. You're back to that boiler. It's seeing those temperatures. It's generating the heat, and you got a lot of mass. You got a lot of power in that boiler. So it works very, very well. Once that sensor is satisfied, it says, okay, I'm done. Normally there's a post-purge that would take whatever heat's left in that boiler, dump it into that tank. So it's not getting wasted. And then we'll go back and turn on our heating system if it's needed. If not, boiler just goes down into shutdown mode. Okay? But basically P1 will be turned on. Whenever we're dealing these two temperatures and that kind of stuff, we'd like to always post-purge and dump whatever water we have either into the heating system or the indirect. Don't leave it in the boiler. It's not doing you any real good down there. Okay. Here's just some different applications. That's one up in the left. It's basically a domestic water situation where you see two very large storage tanks, and those boilers just circle back and forth to the tanks. High efficiency boilers also love water parks in it. Think about it. What do you got? You got 75, 80 degree water coming back to the boiler. It's always in condensing mode. Really nice application. Both of them are good applications when we help you engineer them correctly. Biggest thing you got to remember is you do shorten life expectancy. Yes, we are dealing with stainless steel heat exchangers, but domestic water is rougher than regular hydronic water because there's always impurities in it. The biggest thing people worry about with water parks is who's the chemist that's throwing the chemicals in the pool. That's the guy we got to worry about, and it's usually not the highest guy on the ladder. So it does reduce the warranties on these two applications, but it's still an excellent way of making or heating up these two water sources. The other type of boiler out there is a high mass condensing boiler. We're not real tricky in the hydronic industry. High mass means it holds a lot of water. All right. So basically, it does throw out some of the rules we said earlier. Since I've got this big mass, piping is not as critical because I've got all this water to move around. I mean, I'm not talking 25, 30 gallons here. I'm talking on these type of boilers, 2, 3, 4, 500 gallons. So basically, say it's almost a built-in buffer tank and whatever, but basically is a high efficiency boiler, high mass. If you look at the way the flue is going through here, the coldest water is at the very end of the system. So basically it is condensing the most right there and keeping the whole efficiency, the whole unit very high. And since it is such high mass, we don't have a pressure drop in the boiler, and a lot of these don't even require a dedicated boiler pump. So it's something to look at when you're dealing with the larger boilers, schools, that kind of stuff. Okay. This is sort of a residential version of a high mass condensing boiler. What this basically is, you think about it, we got a tank there, if you want to call it the buffer tank, with the heat exchanger inside, and what they actually do is basically want to call it, just strap the boiler to the side of it, high efficiency boiler. Okay. It gives you all the benefits of the condensing boiler technology because it has a condensing boiler system on it. It also gives you the advantage of the high mass. So now if you have little zones firing on and off, it's not going to bother it because that burner is not going to kick on until you take the stored BTUs out of that tank. Okay. There are different styles of it. Stainless steel fire tube. This one here has to be a stainless steel tank with a copper nickel heat exchanger. This manufacturer's actually been using this same design heat exchanger for probably 30 plus years for domestic hot water. The nice thing about this unit is it does have that capability of dealing with very, very small zones. It also has the capability of dealing with a lot of dirt. There's actually about 3 to 4 inches of area underneath that heat exchanger of just blank space, basically. It's just holding water. That's all it is. So you can get a lot of crap in there before you even start touching the heat exchanger. Okay. It's just an example of it. As you can see, this is Grandpa's piping. Boiler in, boiler out. That's all there is to it out to the system. Okay, so it's a very, very simple system, and it's due to the high mass of the boiler. So it's very compact. As you can see, it still vents in PVC because it is a condensing boiler. when you're dealing with new boilers and new boiler systems, you do not have to go strictly cast iron, 80-some% efficient, or strictly all condensing boilers. It's very easy to put a condensing boiler up front of the system and keep your old cast iron boilers for the really cold days. So what happens most of the time is the condensing boiler handles the heat loss of the building. Remember, we only need, again, going back to the 1% rule, we only need our maximum capacity 1% of the year. So that means most of the time, I think we figured it out the other day, or Ryan did, about 70% of the year we're above 30 degrees.
Yep, but the lower 90% of the year we're above 20 degrees.
Okay, so that means most of the time this condensing boiler is going to handle most of the load. All right, so now you've got a high efficiency boiler on the front end handling that load for about 70% of the year. It's going to make a definite difference in the gas bill. When that condensing boiler can't keep up, when the temperature does get low enough, then it calls on the next boiler. And depending on how those are wired together or whatever, we'll call them next one or two, depending what's necessary. A lot of these condensing boilers have what I like to call the Dinosaur Switch, which basically calls that next boiler on when it can't keep up. Here are just a couple more methods of showing how to do it. Okay, but if you look here on both of them, you got your condensing boilers are the first thing. They're taking the coldest water from that return, going through them, heating the water up. If the water isn't hot enough or sufficient, then we'll start kicking on the standard boilers. Okay, but that's only after we use condensing boilers so we can maximize our efficiencies. That's one way of piping it. There's multiple ways of piping these things. I would spend days on it, but when you get into this kind of stuff, give us a call. Be more than happy to work with you on it, get you piping diagrams and everything else that we've used from past experience. We do not experiment on anybody. We know what works, and we'll help you along to make sure it works. Here's another system just showing this pretty much similar technology. You come from the system. First thing you do is you hit your condensing boilers. You go through. If it's sufficient, it just goes right to the system. It doesn't go into the non-condensing boilers. If that temperature at T3 there is not correct or still too low, then it will go over to the non-condensing boilers to raise it up to get to the proper temperature for that day and out to the system. So a little bit of piping, a little bit of controls, and there's a lot of things you can do with these. You don't have to get into all or nothing routine with condensing boilers. This is very popular with churches and schools. Okay.
There's a lot of supplemental resources. Obviously, you're more than welcome to come to any of our training classes on hydronics or condensing boilers or radiant flow or any of the stuff that Bill or I do. There's also other independent groups you can look at. Radiant Panel Association has some decent data on there. AHRI, if you're already not familiar with it, you can get ratings on just about any new boiler that you want from any manufacturer to see how many BTUs and what efficiency it is. There's lots of hydronic resources. I mean, hydronics doesn't really change. It's been the same way it's been for 100 years. Sure, we got new stuff like condensing boilers, but the fundamentals, they're all there. So Bell & Gossett website is fantastic, all kinds of training videos. The Little Red Schoolhouse over at Bell & Gossett is in Morton Grove. That's the nationwide training center right here in our backyard. Fantastic classes there as well. If you want random help, heatinghelp.com. If you go on that website, you can pretty much post a question about any weird thing you want, and 35 wetheads will respond to you with 35 different answers. And there's some pretty good handbooks available from all the pump guys and all the boiler guys. So there's lots of ways out there to get more information. Our final poll question, and then we'll start reading some more of your guys' questions, is just to rate for us how we did, so we can get a little bit of feedback on how that went. And while you guys are answering that, I'll start asking some of these final questions that went in. Let's see. Fazil asks, in an existing building where the equipment is sized for 180, 200 entering water temperature, can the condensing boiler be used? Can the condensing boiler be run at 180, 200 temperature on cold days? So I don't think you get too many boilers that are sized for 180 or 200 entering water temperature. You probably meant leaving water. If you meant entering, you're probably talking about steam at that point. Because if it's already 200 and I heat it up more, it's going to be steam either way. So you probably meant leaving water temperature. So yes, if you got a boiler sized for 180 degree leaving water temperature, we can certainly replace that with a condensing boiler. And on some days, it'll run at 180. But then with the outside air reset curve, when it's not zero outside, we lower the temperature, we lower the temperature, we lower the temperature, and we get those condensing modes as many hours of the year that we can.
Okay. One other thing for that, just check with the boiler manufacturer. Certain ones will allow you to go to 190, but again, you're dealing with that 1% time. So the more we can keep it lower, just like Ryan said, the lower the fuel bill, whole routine.
Bill types in, our small church put in this type of new boiler system last year with considerable savings. We also installed an outside air reset. However, the contractor had the system set so that the boiler doesn't heat and circulate water until the outside temp is below 55. This can result in a cold church. What is the highest outdoor air temperature I should have them set at in Madison, Wisconsin? The highest temperature will be, when do you need heat? Every building is going to be a little bit different, right? So even at your own houses, some of you people listening on here have houses that are poorly insulated and need to turn the heat on when it's 68 degrees outside. Other people have fantastically insulated houses, and we don't turn our heat on until it's 55 outside. So it really depends on what's going to make your building occupants comfortable, Bill. 55 might be a little bit on the cool side. You're probably going to be somewhere in the 60s. You're probably going to be changing over to the heating system, I would think, for most buildings.
Best thing is ask the little old ladies on the church board. They'll tell you where to start. Ran into that before.
And they'll pick 80 degrees outside, just so you know.
Yeah.
Mark types in, who sells buffer buddy tanks, and what is the typical capacity of a typical tank? Obviously, we sell them, otherwise we wouldn't have talked about them. But the ones that we use are made by a company called Boiler Buddy up in Wisconsin. So we have a good relationship with them for the past 15 years. And they're one of our boiler suppliers also. But Boiler Buddy, if you go to, I think it's boilerbuddy.com, you can see what they got on there.
It goes up to the largest one that we stock is 119 gallons. Once you get up to that, you're talking a pretty hefty volume of water. You really want to see what you're doing with the system at that point.
Andy types an extremely long question. It'll take me forever to read, and it looks like it's about a specific job. So Andy, Bill, and I will get back to you after the webinar here. John, do condensing boilers need pump mounted on the supply or the return side, and does it matter? It's a great question, John. I'm surprised no one else asked it yet.
What we normally like to do is we like to pump into the boiler or circulate into the boiler. Remember, that circulator is designed just to handle the boiler loop. So that pressure drop I'm seeing is in the boiler heat exchanger. So normally our most preferred locations, probably 99% of our applications, is we pump into that boiler. So we're using up the head of that circulator in the boiler where it's designed to be used up. So that's basically the return is the best point for it.
Does anybody else have any other questions they want to type in and have us try to answer? If not, we'll stand for a couple minutes here, and if you do, we'll answer them, and if not, we'll close it down. We do thank you guys for checking in with us today. This is a recorded webinar, so if you got a coworker who needs to see it, I'll have it posted in the next couple hours online on our website, tecmungo.com/training. And if you have any other questions, just holler at us. Our information's up there on the screen. Thank you.